the transfer function look like. We have 5 points, which is VOH, VIL, VM, VIH, and VOL that we are interested at deriving. The ideal characteristics for an inverter, the voltage transfer characteristics for an inverter would have VOH equal to VDD, would have VOL equal to 0, and would have VIL and VIH exactly equal to the switching point, which happens to be at VDD over 2. And this way I will have maximum noise margin high and maximum noise margin low, which are equal to VDD over 2. So my signal, literally, if this is the input signal, هلا هيدي هي VO versus VM. What I'm drawing here is really Vn versus time. Okay, and let us map the points بس حتى تكونوا مرتاحين بالconcept of how where these points fall. So when Vn is equal to VDD here, for example, and this is a DC characteristic curve, and this is if I stay at a specific point for a very long time. So let us say I stay at VDD for a very long time, okay, then the corresponding output, okay, here in response to this block should be 0 here, and then it should rise here, and then it should fall, and it should rise again. Okay, so this is the response of V out as function of time. Hello. When we say that the noise margin high is equal to VDD over 2, and the noise margin low equal VDD over 2, this means that I can tolerate an input signal that has fluctuations as high as VDD over 2 in both directions, and my output will still be perfectly the same. Okay, so this means I can tolerate noise up to the midpoint while my output will still be VDD if I give it enough time to respond. Okay, so these are the ideal characteristics. Okay, anybody has any questions? Okay, so let us now look at this sketch here. So here they're telling me, what if I have a switch, okay, and this switch opens when Vn is 0 and it closes when Vn is high. Then when Vn is low, the switch is open. And under this scenario, what do we expect for the resistor-based inverter, the output to be? What is the current flowing from VDD? It's 0, right? So if we have here, this will be V out, therefore, will be equal to VDD minus IR, and it will be equal to VDD. So when the switch is open, it has isolated the output from ground, and the resistor, due to the current being equal to 0, really is the only device connecting the output to a supply which happens to be VDD, so it will pull it up fully to VDD. Okay. Now, the other scenario happens when Vn is high. When Vn is high, this switch is characterized by some small on resistance. Okay, and ideally it should be a short circuit, but it has a small on resistance. So the device is from one side connecting the output to ground, and the load resistor, which is typically larger, is connecting the output to VDD. So by virtue of voltage division, V out is going to be equal R on over R on plus R times VDD. Now, if R on is small, meaning smaller than R, this means that VO will be greater than 0 but small. VO will be small, right? So VOL, let us say, will be around 0.1 or 0.2 volts, for example. Okay, so under this condition, if the device is strong enough, its R-on will be small and it's going to pull the output. The output will favor the low. Okay, now how do we implement this switch? We implementing using a transistor that has a small on resistors. Why? because if Vn is 0, the transistor, this is an NMOS, the NMOS will be off, and if Vn is VDD, the NMOS will be on and will have a small resistance. Okay, so this is how we implement this switch using a transistor. Okay, using a transistor. Okay, this is one implementation for the inverter. Another inverter implementation is to use complementary switches. Where these switches respond differently to the polarity of the input. Yani this is active. The pull up is active low, and the pull down is active high. So when the input is low, okay, the pull down switch will be off, and the pull up switch will have a small R on, okay, and under this scenario, the output will be connected to VDD by virtue that the DC current flowing from VDD to ground is equal to 0. Since I equal to 0, then my V out will be equal to VDD. هلا لما بنستعمل الديفايس equations للPMOS والNMOS, when we use them as transistor, we will see also how this qualifies the same. Okay. Now, when the input is high, the pull up will be off لأنه active low, and the pull down will be on لأنه active high. And so I will have the output isolated from VDD, but it will be connected to the V out by a resistor, by virtue also that the current equal to 0 flowing between VDD and ground. The voltage drop will be 0 across R on, and V out will be equal to 0. Okay, so therefore the output when Vn is low is really VDD, and the output when Vn is high is really equal to 0. So this type of inverter allows me to have an output that fully switches between VDD and 0. And how are the switches implemented? They can be implemented using PMOS for the pull up and NMOS for the pull down transistor. Okay, so هيدا البول up اللي هو بيكون between VDD and out, and the pull down is between out and ground. Okay, طيب, great. Anybody has any questions? Okay. So let us now, we will start to derive the quantities that characterize the voltage transfer characteristic curve of the resistor loaded inverter. Resistor loaded inverter يعني عنده pull down وعنده resistor between VDD and V out. لما ال pull down is off, resistor pulls it up, else the device will fight the لما ال pull down is off, the resistor will pull things up, else لما ال pull down is on, it will fight the resistor and will pull the output down. Okay, so we are going to try to solve for VOH, VOL, VIH, VIL, VM, noise margin high, and noise margin low. So then we are going to study the average power dissipation of this inverter. So for this type of inverter, the first step, we enter here. Okay, the first step for this type of inverter is to solve for VOH, and we will look at the slides in a second. Why we solve for VOH? Because the easiest thing for me to solve for is to solve for when the device is off, pull down off, so Vn equal to 0 less than Vtn. Okay, great. The most important thing in this type of inverter is to look at the pull down device and say, well, I have VGS minus VT, I have VDS, and I need to determine the region. Okay, and then I know that IR is equal to IN, and IR is nothing but VDD minus VO over R, and IN is equal to the current of the transistor based on the region in which I am operating. Okay, so for Vn equals 0, the pull down is off. So let us agree on one thing, which is for this inverter, this is Vn from here to here. This is the NMOS, this is the source node. Let me draw it in blue. Okay, so this is the source node of the NMOS device. And here I have Vn. Okay, and so VGS minus VT, VGS is equal to Vn, so it's equal to Vn minus VT, and VDS is really equal to VO. Okay, now when Vn equals to 0, the device will be off, and in this scenario, I'm going to set this current to be equal to 0, and this will be if and only if V out equal VDD, يعني VOH will be equal to VDD. Okay, فإذا VOH I solve for it when the device is completely off or when the input is low, and this turns off the device and the RD will pull up the output to VDD. So خليتي point we finished VOH. Anybody has any questions? طيب. And now we're going to solve for the second point, which is VOL. Okay, so if I want to solve for VOL, I have to look at the, now what do I set the input? I set the input to be equal to VOH, and we said inside the circuit, the chain of elements that we have, or the chain of inverters will feed each other, so the highest voltage on the chip can be VOH. So to solve for VOL, okay, so to solve for VOL, so this is the second point, we try to solve for VOL, and for this we set Vn to be equal to VOH, which in this scenario is equal to VDD. So now I will have VGS minus VT for this inverter equals to VDD minus VT, and my VDS is equal to VOL. Okay, this quantity is small and this quantity is large by virtue that VDD minus VT is greater than VOL, and therefore the region which I'm operating in is linear. Okay, and with this linear region now I can solve again the equation that says IR equals IN, because the current is flowing down and the resistor is the same as the current that will flow in the device, and so VDD minus VOL over R is equal to, now the current in the linear region equals half K prime W by L times 2 times VGS minus VT is VDD minus VT times VDS, it is VOL minus VOL squared over 2. Minus VOL squared, pardon me, half is outside here. Okay, minus VOL squared. Okay, in some scenarios, if we tell you, okay, if we say we can ignore, if VOL is very, very small, we can ignore the quadratic term. We can ignore the quadratic term. Okay, and we solve the equation linearly, and بتصير equation is linear in VOL. If we don't tell you that, then you solve for it with the quadratic term. Okay, so this is solving for VOL. Anybody has any questions? Okay, so let us, yes, go ahead, Karim.
How did they both when they're unloaded? يعني ما بيكون في شيء على الVO.
Okay, let us, when we study the VTC characteristics of the inverter, we only study, for our purposes, we are going to only study the transistor, the pull-up and the pull-down devices. Okay. هلا أنا assume I have two inverters. How things happen in real life? Only those two devices. The loading affects me only from a delay perspective. يعني أنا if I have the first inverter at DC, okay, driving the second inverter, okay, if I'm performing the DC analysis, شو الcurrent that flows here to the gate? I have infinite impedance, right? So I study the inverter itself as a DC characteristic, okay? بس the two devices, okay? Is that was your question?
Yeah, that's my question.
Okay, excellent. هلا بالديلي حيكون عندي capacitor على الاوتبوت representing the load of the next stage. Okay? بالديلي I will have a capacitive load from the next stage that can affect me. For your purposes, we tell you what is C load for 311. Okay? طيب, excellent. هلا let us now take a look at the slides and then continue deriving the other quantities. So here in this slide, they are solving for me what VOH is, okay? And in this second slide here, we are solving for the characteristics of VOL. يعني حطينا VGS equal VN equal VOH, and we're trying to solve for VOL. We said the MOSFET will be in the linear region. We put the current equations here, ID, what it is in terms of VDD and VOL, and we set ID equals to IR, and then we solve for this equation here. And in this slide, they really tell me the full quadratic equation, what it would be. Okay, يعني عاطيني ال AX squared plus BX plus C, that is written, well, at least it is written for me here. And they represent it in terms of the ratio of VOL over VDD, and then they solve for the roots. So I get what X should be. هلا طبعا it is easier for you to write the AX squared plus BX plus C and find the root, and this is too convoluted. And then they're telling me that if VOL is expected to be much smaller than VDD as a quantity, let us say 0.1 VDD, then VOL squared would be almost 0.01, let's say volts, pardon me, then VOL squared will be 0.01 volts, and so I can drop it. And under this constraint, I will end up with a linear system where VOL will be equal VDD over 1 plus KRD times VDD minus VT. K is the K that appears in the equation of the transistor. هذه هي K prime W by L يعني. Okay, so this is K prime W by L. RD is the pull-up resistor, and VDD and VT are the quantities of the VDD and VT of the device. Okay, so هيدي إذا اعتبرنا إنه ignore the quadratic term. Okay, great. طيب, هلا now we're going to look into the second problem that he wants to solve for. He wants to solve for VIL. طيب, at VIL, the transistor has just turned on. يعني VIL فينا نعتبرها هي VT plus a small delta. It just turned on. إذا هاي ال VT هيدي ال VIL. And therefore the output is still high. Okay, so the output is still high and the input is still small, and so we agreed last time that this would be in the saturation region. هلا نحن what we're going to do, we're going to set VGS minus VT, VDS, and this is the region. So VDS is high, it's almost VOH minus, and VGS minus VT is really some small delta, so this is big, this is small, so this is greater than this, and we will be operating in the saturation region. يعني من ال characteristics نحن قلنا إنه saturation is here, it's gonna be saturation, and if you want to inspect it, this is what we will see here. طيب هلا the issue with VOL, with VIL is that it has more unknowns that I can handle or solve. ليش؟ لأن أنا الهيدا is in saturation, this device is in saturation, and I want to set IN is equal to IR. So I'm going to say half K prime W by N times Vn minus Vt all squared. This is going to be equal to VDD minus VO over R. So I have one equation, two unknowns. Okay, so I cannot solve for it. What we do is we rely on the relation that dVO by dVn at Vn equal to VIL is equal to -1. Okay, I differentiate this equation star. So I do d star by dVn, and I plug the value that the input is equal to VIL. This will provide me equation 2, and this is of course equation 1, and I can now solve for the relation. فإذا we will start with this equation here, where we say that ID equals to IR, okay? And we are going to differentiate. What they did, they grouped VO on one side and Vn on another, or you can differentiate on the go. يعني D by dVn on this side you will get what? 2 ضارب half بتروح بصير عندنا K times Vn minus Vt. Okay, on this side if I differentiate by dVn, okay, so this will drop down, and then on the other side we will have minus VO over RD, الكونستانت VDD بتروح، so حيكون عندنا -1 over RD times dVO by dVn. Okay, so now what I can do, I can plug in or evaluate this equation when Vn equals to VIL. Okay, so I will end up with the relation that I am looking for. Okay, so I will end up with, if I plug in, what would I substitute dVO by dVn? By -1, right? هيدي بتصير -1 وهيدي الVn بتصير VIL. Okay, so let us differentiate this equation. So I have here half K times Vn minus Vt squared equal VDD minus VO over R. I differentiate with respect to Vn. I will end up with K into Vn minus Vt is equal to -1 over R times dVO by dVn. I will plug in and evaluate when Vn equals to VIL. So I will end up with -1 over R times this quantity becomes -1. Okay, and at the input I will end up with K into, this would be VIL, and I will plug VIL. Okay, and this will be the minus VT. Okay, so therefore I will end up with VIL equals to 1 over R times K plus VT. Okay, حدا عنده سؤال؟ فإذا we started with the equation, we differentiated it with respect to Vn, then we evaluated it at Vn equal VIL. Derivative dVO by dVn, it is -1 by virtue of the definition, and Vn I plugged VIL for it and I solved for VIL. Okay, Great. Okay, let me clear. Okay, so now we want to solve the third point. We solved for VOH, we solved for VOL, we solved for VIL. The fourth point that we are going to solve for is the point VM. At point VM, Vn is equal to Vout equals to Vn. Yani the device will have VGS minus VT and VDS, and the VGS minus VT will be Vm minus VT, and the VDS will be Vn, and the region will be the saturation region. Why? Because this quantity is greater than Vm is greater than Vm minus Vt. And by virtue of the VTC, we know that this is going to be inset. Okay, هلا طبعا في يكون design very bad and it may not meet this criteria, but at Vm, the region may not all of it be inset, but at Vm, I have the specific property that VGS minus VT equal Vn minus Vt, which is Vm minus Vt, and VDS equal Vm. So it enforces the saturation condition. Great. So I will end up writing that ID equals IR, which is half K prime W by L times Vm minus Vt square is equal to VDD minus Vo, which is Vm over R. Okay, so this is the equation. It's a quadratic in Vm. Okay, and we will end up with a solution for Vm that depends on K, R, VDD, and Vt. طبعا we'll have two solutions, but we will pick the one that is greater than Vt. Okay, we'll pick the solution which is greater than Vt. Okay, طيب great. هلا we are going now. حدا عنده سؤال? These are just procedural. It's almost repetition for 3 times. So now you need to look at the analysis of VIH. The analysis of VIH is a little bit convoluted. So I'm just going to cover the region of operation. Yeah, let us say, for example, we know VO and we want to find VIH, or we have some information that simplifies this problem. Let us analyze the region. VIH is in the low gain region, and typically its output is very low, and we would have skipped the entered into the linear region because the NMOS device is going to be characterized by VGS minus VT and VDS. My VDS would be VOL plus. It's a little bit larger than VOL, and my V input will be VGS minus VT will be VIH minus VT. Typically in this region, this is larger, and so the device will be in the linear region. Okay, so the device will be operating in the triode. Accordingly, we will have half K prime W by L times 2 times Vn minus Vt, or VGS minus Vt times Vo minus Vo squared is equal to IR, which is VDD minus Vo على RD. كمان here we have two equations, one equation, two unknowns, and so in this consideration, I will have to rely at the fact that dVo by dVn at VIH is equal to minus 1. So in here, I have to differentiate both sides by dVn, okay, of this quantity here and this quantity here. And of course here, since VO, يعني حتصير VO squared, for example, بتصير 2VO dVo by dVn. So it is a little bit convoluted, and they show us here. And then this is UV, so it will be U prime V, which is VO plus V prime U. So V prime is del VO by del Vn, and this is U. And at the output, it will be minus dVo by dVn over RD. And if we set dVo by dVn equals to minus 1, we will end up with another equation that relates VIH and VO. Okay, so what we end up having here is the second equation after differentiation that relates VIH and VO, and I have the first equation before differentiation that relates VO and VIH. So here I will find one as function of the other, okay, and then plug it in back into this equation, specifically VIH minus VT. I will plug it, I will change it here, okay, and I will end up with this complex equation star that is only in function of VO, and therefore now I can solve for VO and obtain the solution for VIH, which ends up being this equation here. Okay, so this is the equation for VO, and this is the solution for VIH. Okay, so this way we would have identified all 5 points of the, not the edge of linear, this point VIH, and this is the point VDD. When the input is VDD. There is one more point, which is point C, which is the onset or the edge of saturation. Okay. And at this point, at the edge of saturation, VDS would be equal to VGS minus VT. Okay, so VO would be equal to Vn minus Vt. Okay, and I can, since it is at the edge of saturation, I can solve for it by setting In equal to IR and taking this thing into consideration, that the V out is equal to Vn minus Vt. I will end up having one equation, and I can solve for the voltage, the output voltage at edge of saturation. Okay, but this point from inverter characteristics, from digital characteristics, it is not significant. I don't really care for it, because what I care for the inverter is the noise margins and the switching threshold point. Yani at what point the strength of the pull up and the pull down flips. Okay, that's what I care for the inverter. And if you notice, this really looks like the amplifier circuit, but the region of the operation is different. We are really operating in this region as the logic 0, and in this region as the logic 1, and this region here for me is forbidden. It is not a good operating region. Okay, so I do not operate my circuit in this region at all. Okay, VM, I only find it to know how symmetric the pull up and the pull down capabilities of my inverter, but I do not operate at it. And also my input signal, if you notice, this is Vn. When I want to apply Vn as function of time, I'm going to apply Vn either high or low. Okay, so I try to operate within the logic 0, okay, or the logic 1. So I operate either at this range or at this range here. I do not operate in the forbidden region. And I hope that any noise will be within this margin. Okay, so any noise will be within this margin. Okay, for the digital operation. Clear? Anybody has any questions? Okay. Okay, great. So let us now then jump to the next slide. هيك بنكون غطينا ال characteristics للinverter. Next, we need to look at the power dissipation and then the delay. يعني أنا في عندي 3 concerns for the I have 3 concerns for the design. أول شيء النويز margins, okay, and the value of the operating logic VOL and VOH. So noise margin low, noise margin high. Then يعني noise with operating points. Then the second, and the DC characteristics, the second is the power dissipation, how much power this design dissipates if it has good noise margin. And then the delay, لأنه I need to meet speed requirements. On my chip, it has to operate at a certain frequency, and it should not drain the battery power. So I need the energy in the battery, so it should not have too much high power. And these are the 3 concerns that we typically study in a design. So let us look here at the static power dissipation of the resistor-based inverter. So for this resistor-based inverter, when we say static power, it means that when my output has switched and it's sitting in a specific state, the two states for the output, VOL and VOH, what would be the power of it when it is a stand-alone? I'm not doing any operation. My phone is has done some functions and now its inputs have settled. Is the draining power? How much power is it draining when there is no activity? Okay, so this is the static power dissipation. Typically, when there is no activity and no transients, we study it at DC. So let us look at the inverter. When the input is high and the output is low, so when the input is high, meaning VDD in this case, and the output is low, VOL, what is the current ID that is flowing from VDD? Do I have a current ID that is flowing from VDD? What is it?
Zero. VDD minus VDD over RD.
So for the output is VOL. Okay, let us revisit the switch here that we saw a bit ago. And this is the resistor-based inverter. So when the input is high and the output is VOL, the pull down is on and the resistor R, it is always connecting the VDD to output. So do I have a current I that flows from VDD to ground? Is I zero or not?
It should be. It shouldn't be, sorry. لأنه إذا VO low يعني في between
صح.
اتحاد في current.
I have two resistors. هيك بدكم تفكروا فيها. I have a path between VDD and ground. Okay. Once I have a path between VDD and ground, then the current is different from zero. I have two resistors here between VDD and the ground. So I is VDD over the sum of the resistors, right? Or I have VOL different from zero. Automatically, this will tell me that I have a path between VDD and the ground. Okay. Now, the scenario in which I will not have a path between VDD and the ground is in this scenario where the pull-up is off, okay, and its current is zero, and therefore VO is connected all the way to ground. So VOL here is zero, right? So in this scenario, my current will be zero. Let us look at the same resistor-based inverter. When the pull-down device is off, when the input is low, the pull-down device is off, okay, its current is equal to zero. Therefore, the output is fully VDD. The output is fully connected to VDD. Okay, هلا نحن okay, when the output is fully connected to VDD, in this scenario I is equal to zero and there will be no power dissipated. In this scenario, the pull down is on and the resistor, of course, is always on, right? Because it's a resistor, and therefore the two are fighting to connect the output closer to ground or VDD. This R on is small, so VOL will be different from zero, but it will be small. Once the two are on, then I will have a current. They will allow for a current to flow from VDD to ground. Is this clear? Okay, so let us then revisit now in the context of the resistor-based inverter for the case when the input for the case when the input was high, okay, when the input was high, the NMOS device was on, okay, and so there was a current, okay, where ID equal IR, it was different from 0, and we used this to solve for VOL. Okay, so this is when the output is low. Okay, so under this scenario, we have a current flowing between VDD and ground. I know that this is on and the resistor is always a path, so there will be a path between VDD and the ground when this is VDD. Okay, so in this scenario, if I am given VOL, if somebody tells me VOL for this is this much, what is the current that is flowing from VDD? إذا عطاني VOL بس ما عطاني transistor characteristic, did not give me what W by L is. Can I find what is the current? But I have RG value. Can I find what is the current that is flowing from VDD?
بس Ohm's law VDD minus VOL over R.
Exactly. So the current will be equal to VDD minus VOL over R. Okay. So great. لكن نحن بالresistor based inverter, we are going to have two scenarios for the static power dissipation. The first scenario is when the input is high, when I have input VDD, and the output is low, this is VOL. Okay. In this case, the current ID flowing from VDD will equal to VDD minus VOL over R. Okay. And the power dissipation will be equal to what? It will be equal VDD times ID. Okay. And then the second scenario which we will have will be when the input is low, when I have a 0 here, and this is V out equals VDD. Okay, automatically we know that this device is off, and by virtue of IR will be equal to 0. Once one of the devices is off, let pull up, yeah, pull down, there will be no path between VDD and the ground, so the current will be equal to 0. So the power in this scenario will be equal to VDD times 0, which is equal to 0. فإذا في عندي two states. If my input is high, my output will be VDD times ID, which is equal to VDD times VDD minus VOL over R. And if my input is 0, my power will be 0. يعني in half of my states, if I live in 50% input high, 50% input low, then my power is going to be the average of those two powers. If my states are not balanced, if I say I'm 70% input high and 30% input low, then my static power will be 0.7 times this quantity and 0.3 times 0, plus 0.3 times 0. Okay, so it is the average, the statistical mean. Let us now look here. So they say, well, when the output is low and input is high, I am approximately, my power is this quantity is approximately VDD squared على RD. Okay, and when my input is low and my output is high, the pull down is off, and so the static power dissipated in the circuit is equal to 0. Okay, so the average static power will be the average of the two if the inputs are equiprobable. Yani high and low states are equiprobable. Anybody has any question? So most importantly, anytime a current is flowing بين ال VDD والground, يعني I will have power. Otherwise, if the pull down device is off, then I will have the power equal to 0. Okay, طيب, great. هيدي static power. Just like there is a static power, there is also dynamic power. شو يعني dynamic power? يعني أنا I have the inverter, as you just said a little bit ago. Well, this inverter is driving another inverter for which I see the capacitive load. So it's driving some load capacitor here. What happens when the input goes high? What happens to the output? Sorry, this is the inverter. This is a CMOS inverter now we're talking about. When the input goes high, what happens to the output? It will start as high and it's going to discharge, right? To go low. And then the input goes low again and the output will go high again. Then the input goes high and the output will go low. So this activity is really what's happening. The load capacitance is being discharged and charged. يعني عم بروح current على الكاباسيتر to charge it and then it is being discharged. And we'll talk about this in details later. So charging and discharging the capacitor will result in currents being drained from VTT or in some energy being dissipated from VTT and therefore in a power dissipation. And this power dissipation is function of the frequency of charging and discharging the capacitor. يعني if the output is being discharged and then it is being charged, the operation of charging and discharging is going to dissipate some energy, and then when everything is steady, the circuit itself will dissipate some static power. يعني هون the output has fully reached VOL، ما بقى في energy عم تروح على الكاباسيتر، خلص صرنا كأننا نحن we are in DC. But at those two edges I am performing some dynamic operation where I am charging, increasing the charge in the capacitor or decreasing the charge. هون increasing the charge or decreasing the charge in the capacitor. Okay, so نحن هلا عم نحكي عن dynamic activity where there is some dVO by dt across the capacitor at the output. Okay, هيدي هي dynamic power dissipation. Okay, the static power dissipation is when the output is a steady state, there is no dVO by dt, we do not consider